So now you are. Thank you very much.
Well, thanks, Isabel, for the introduction. I want to thank Isabel and Jose for the invitation and yeah, giving me the chance to give this talk here. It was always like some of my favorite conferences were always in Spain. Unfortunately, we have to do it like this, and as we said, hopefully, like from next year, we'll be back to normal. Okay, so my talk is on ancient solutions to mean curvature flow, and all the work I'll be talking about is joined with Matt Langford, who's also here at the University of Tennessee, and Giuseppe Tinaglia, who is at King's College in London. Okay, so just in case for some reason that might not work on mean curvature flow, I want to start by a brief introduction. So what do we have with mean curvature flow? We have a family of hypersurfaces that moves with speed equal to its mean curvature. Okay, so here, this is the equation that we should satisfy. M and T here is a family of hypersurfaces, and if I consider them parameterized by x, then x should satisfy dx dt equal to the mean curvature vector. Okay, the mean curvature vector is defined here, and we write it as a scalar mean curvature times the normal. Okay, so the convention that we use is with a minus. So you should think that, well, I have examples, but convex things should shrink. Okay, so the special case where n equals 1, we have the curve shortening flow. Here, the mean curvature is just the curvature of the curve. And in this example here, we see a curve, and the arrows that point towards where the curve is going to move. The length of the arrow means the bigger the length, the bigger the speed. Okay, so the more the curve curves, the faster it's going to move. Okay, and this is a picture of time slices of a curve evolving under curve shortening flow. We'll mention it a bit later. Curve shortening flow is this very nice property proved by Grayson that when you start by any simple closed curve, this curve is going to evolve by curve shortening flow. It's going to become convex, and it's going to disappear to a round point in finite time. Okay, that's why you see here we started by a weird curve, and later in time it becomes almost circular. Okay, and it's going to disappear to a point. So in higher dimensions, of course, the mean curvature is the sum of the principal curvatures. Okay, so here we see like an example of dimension 2. The mean curvature is kappa 1 plus kappa 2, the two curvatures, okay, which is the largest and the possible curvature of a curve I see intersecting my surface with a plane that is parallel to the norm. Okay, so standard examples are that of the shrinking sphere and the shrinking cylinder. So if I take a sphere and I flow by mean curvature flow, the sphere is going to remain a sphere and it's going to start shrinking. It will eventually disappear to a point. With a cylinder, I start with a cylinder, and the cylinder remains a cylinder, but its radius goes down, and eventually it will disappear in a line. And mean curvature flow has a nice property that it preserves symmetries. So here, that's why if I have a sphere, it's going to remain a sphere. And it's easy to compute the radius. Okay, you just solve like a simple ODE because it's only the motion of the sphere is determined by just the radius. And the same thing with the cylinder. Okay, so why do we care about mean curvature flow? Mean curvature flow has various applications, not just, we're going to talk about the physics one we mentioned here, and there are like math ones. So they started investigating mean curvature flow as it appears in the description of the evolution of interfaces which arise in several multi-phase physical models. It is also used a lot in material science as mean curvature flow is used to model cell, grain, and bubble growth. And finally, it's also been used in image processing for using mean curvature flow to change an image. Now, for me, it's more interesting the geometric applications of mean curvature flow and in general curvature flows. Okay, so when we talk about curvature flows, in general, we mean that the speed is not necessarily the sum of the principal curvatures, but some other function of the curvatures. So the first main application, probably considered one of the most important, is that they can be used to obtain classification theorems. This is done via the use of certain curvature inequalities that are preserved under specific flows. So for example, this property has been used by Husken and Husken and Sinasari to classify convex and two convex surfaces. Okay, two convex means that the sum of the two principal curvatures are positive. It has also been used in dimension 2 by Brendel and Husken to classify such surfaces in manifolds, but there they had to use a different curvature flow, okay, by the harmonic mean. Now another application is that we can use geometric flows to prove geometric inequalities. This is done by using appropriate monotone quantities. So in fact, usually it's a very useful thing to be able to find some quantity that is monotone under the flow. Then, you start by a surface, you look at this quantity, you know that this quantity is monotone under the flow. So if you know the sign, let's say, of this quantity at the limit, then you can say something about the sign of your original surface. So this has been used to prove Alexander-Fenchel inequalities and isoperimetric inequalities by Andrews and Schulze. And also there's a very interesting application by the Garoff monotonicity of the Hawking mass. This is under not mean curvature flow, but inverse mean curvature flow. So the speed is equal to 1 over h. And the Hawking mass is an important quantity for general relativity, and it was shown by Garoff to be monotone under inverse mean curvature flow. This fact was used by Husken and Ilmanen to show that this is indeed the case under a weak formulation of inverse mean curvature flow, which holds in a very general setting, and this was the main tool they used to resolve the Riemannian-Penrose inequality, which again, it's a very important it was a very important question in general relativity. A third application is producing stationary solutions. So minimal surfaces, when I take surfaces that have mean curvature equal to 0, they are stationary under the flow. Okay, the speed is equal to 0. So these surfaces can be produced if I start by any surface, and I can show that I can flow by mean curvature flow for all time, then the limit will be a minimal surface. So this has been used by Brian White and Brendel Husken to produce minimal surfaces. And I've also done a work with Moore in a more general setting to show that similar things can happen in Lorentzian space, where the minimal surfaces are replaced by what are known as mots. Okay? These are boundaries of black holes. Okay. Right. So the big issue of mean curvature flow is that the flow does not exist for all time. And it does not exist for all time because the mean curvature goes to infinity in finite time. We've seen that this is the case with the spheres and the cylinders, but these are nice examples because the whole surface has disappeared the moment that the singularity occurred. A more interesting example is that of the neck pinch, which is depicted here. So if you start by something dumbbell shaped with a tiny neck and big spheres on the side, then under mean curvature flow, the neck is gonna start shrinking faster than the spheres do, and eventually this neck is gonna pinch off, creating a singularity. Okay, and in fact, since the mean curvature flow satisfies the avoidance principle, which says that if you have two surfaces that are disjoint, then they will remain disjoint. This implies that singularities should form on any compact surface, right? So if you have any compact surface, you can put a big sphere around it. We know that the sphere is going to disappear in finite time. Therefore, something should happen to your surface in finite time. Okay, so we want to study the singularities. And again, like here, I said singularities are high curvature regions. Okay, so we call singularity the time where the mean curvature is going to go to infinity. So when we want to study, then we want to go a little bit before in time and look how the surface looks like. And we do this by performing a parabolic rescaling about a sequence of space-time points approaching this bad space time point. Okay, so approaching the time and the point where the mean curvature goes to infinity. So we do this by scaling time and space appropriately in a way that at the limit we still get a mean curvature flow. And additionally, this mean curvature flow has the property that it is defined in an interval of the form minus infinity up to t. Such a solution is called an ancient solution. So ancient solutions work as the tangent cones. When we want to study singularities of minimal surfaces or of surfaces in general, you just perform a rescaling in space, and you get a tangent cone, right? Or you get a cone, and then you want to study the cone to understand the singularity. So here you do this time and space, and you get an ancient solution. Now, sorry. If you do the scaling in an appropriate way, in not every time, but in certain cases, you can get ancient solutions with even more properties, and in particular, ancient solutions that move by symmetries. These symmetries are either translation or dilation. And in that case, we have this mean curvature flow can be, instead of described by parabolic PD, can be described by elliptic PD. And I'll say a little bit more in a second. Okay, so since, as we just mentioned, to study singularities, you make this blow up and you create an ancient solution. The ancient solutions, they model singularities of mean curvature flow. Therefore, we want to understand how the ancient solutions look like. And the interesting question is to classify all ancient solutions. Now, the question in this generality is impossible to answer. And what do? We start imposing certain geometric conditions to at least be able to answer the question in these cases. A first condition that is very common to impose is convexity. This comes from the fact that singularities of mean convex solutions to mean curvature flow, they are modeled by convex ancient solutions. Okay, so it might sound like something very restrictive, but in fact, if you just want to look at mean convex, mean curvature flow, all the singularities will be convex. Also, not all the time, but often we're going to look at compact solutions, in which case we're going to assume that the final time is 0. Okay, you can, mean curvature flow, you can translate time and you still, you haven't like messed up the equation. Therefore, we can translate time and make sure that this capital T is equal to 0. Right. Then we can also look at these special solutions, which I said before that they move by symmetries of the equation. These are called Solton solutions. And of these Solton solutions, in particular, we're interested in the following two: the shrinkers, which move by dilation. So you see here the T slice is just a scaling of the -1 slice. And the mean curvature is equal to position times the normal. Okay, the scalar mean curvature will be position dotted with the normal. And this is what I meant before when I said that we don't have to study a parabolic PD, but an elliptic PD. Okay, so here we will have the mean curvature being prescribed via the position and the norm. The second category is the translators. The translators, here we see that each time slice is just a translation of the zero slice. So we have a surface and just like moves in space by translation. And here again, I can take one slice, M0 slice, and we have that the mean curvature is equal to the normal dotted with a given vector, okay, the translation vector. Again, turning the parabolic problem into an elliptic one. All right, so let's see some examples. The very famous example in curvature and flow is the Grim Reaper. The Grim Reaper is a translating solution. Here, I draw it translating to the right. The Grim Reaper is a graph. It's a graph of the function x goes to minus log cos of x, and it lies between minus pi over 2 and pi over 2. When moving by mean curvature flow, this graph will just move with speed 1. Okay, so this here will be the GT. A compact example for curvature and flow, ancient solution of curvature and flow, is what is known as the Ankeran oval or paper clip. This solution can be described as follows. The T slice, here GT, is given by this equation. So cosine x equals e to the t hyperbolic cosine y. Again, this is a solution that lies between two lines of width pi. And as you go to minus infinity, on any compact set, you would see two parallel lines. And in the tip regions here, you will see Grim Reapers forming. Okay? How can you see what is happening at the tip? You have to take this point, you look at a time t, and take this point, you translate it to the origin. And you do this for a sequence of times t going to minus infinity. Then what you see is a Grim Reaper. Okay? So this is why we say this angular oval looks like two Grim Reapers coming from infinity, coming together. And again, here we see the application of Grayson's theorem. This is a convex curve. It will eventually disappear to a round point. Okay, so if you change here the hyperbolic cosine to a hyperbolic sine, you still get an ancient solution known as the hair clip solution. This now is a non-compact solution, and it's also non-convex. The picture here is a bunch of Grim Reapers coming from above and a bunch of them coming from below, and joining up nicely here on straight lines. This solution also is not, exists for all time in plus infinity as well. And as we convert, as we let the time go to plus infinity, we're gonna see a horizontal line. Okay, so this is an example of what I said. If you have a solution that lives for all time, then in the limit as t goes to plus infinity, you would see a minimal surface. Okay, here you will see a line. All right, so in fact, for curvature and flow, there are very nice classification theorems. Hamilton, Scalable, and Cesium, they showed that if you consider compact, convex, and embedded ancient solutions, then the only ones you get is the shrinking circle and the angular oval. I forgot to mention this, but I'm always going to be talking about embedded solutions. Right, now, we also later wanted to remove the compactness hypothesis, and we showed that you actually can do this if you allow to add two more solutions, and that is the Grim Reaper and the stationary line. Okay, so now we know that any convex embedded ancient solution is the shrinking circle, the angular oval, the Grim Reaper, or the stationary line. And in this in this proof that we gave, we also gave a new proof of the Hamilton-Scalable theorem by using, instead of PDE, so they had a lot of PDE in their proof, especially like doing using a Lyapunov functional, again like this, a functional that was monotone under the flow, and we're able to exploit the limits to come up with what an ancient solution should satisfy. OSB used mostly Xu-Wang's dichotomy, which is actually like very crucial in our work. That's why I want to mention it. Right. So what does this dichotomy say? It says that there are two types of compact convex ancient solutions. We have the ovaloids, which are the ones that sweep up all of space, and the pancakes, which are solutions that are confined between two parallel hyperplanes. So here in these two pictures, we see an example of an ovaloid, here, a rotational symmetric one, and an example of a pancake, again, a rotational symmetric one. In this case, for the rotational symmetric examples, the ovaloids case was first described by Brian White, but he had a very brief description, and then Hasselhoff, Herskovits, they provided a more detailed construction, and finally, Angel, Scalable, and Cesium, they gave a very, very detailed description of the rotation symmetric example, giving precise asymptotics, meaning how, when I go to minus infinity, how does this, this point grow? How does that point grow? This actually was very crucial for their uniqueness theorem, which I'll mention in a second. For the pancakes, the fact that ancient solutions exist that lie between the parallel planes was done by Xu-Wang in the same paper where he proved the dichotomy. And later with Matt and Giuseppe, we gave a precise description of this rotation symmetric pancake. Okay, so what do we know now? What do we have about classification? First, we have a very nice theorem on the classification of the sphere. So this says that if I have a compact convex solution and I have some additional geometric condition, then I only get the shrinking sphere. This is a theorem of Hoskin and Sinestardi, and here when I say this certain geometric condition, so for those that know, this is like the type 1 condition. This, you can phrase it as many different conditions. You should think of the diameter. The easiest I think to think of is that the diameter as you go to minus infinity grows like square root of minus t. Okay, so the time, remember here, everything disappears at time 0, so the time is negative, and the diameter should be of the order of square root of minus t. Equivalent would be the way that the curvature goes to 0 as we go to minus infinity, the eccentricity, there was like the isoperimetric ratio, they have like a bunch of equivalent conditions. However, Hershkovich and Matt, they've also given some more conditions that add to this theorem. And very recently, Stephen Lynch, he was able to remove the compactness hypothesis here. Okay. Now let me say, as I didn't mention this, but let me go just back. Here in dimension 1, all of these conditions, okay, the compactness will removed, but then you have to add 2 more solutions. But let's say here, convexity and embeddedness are both necessary, okay? Convexity, we've already shown the hair clip solution, okay, the cream river is going up and down. So this is an example that is non-convex. And embedded is also necessary because there are these Ambrose-Langer curves that look like flowers, okay, that's kind of like have some certain symmetries that are non-embedded, and they actually like self-similar. Okay, so here also this some geometric condition is necessary because of the existence of the rotational symmetric overload, which is not a sphere. So what do we know about that? This is a theorem by Angelos, Kalopoulos, and Sesum, where they showed that there is a unique closed non-collapse and uniformly 2 convex overload that is not a shrinking sphere. So let's see these conditions. Non-collapse, you should think of non-collapse, just think of an overload, just think of something that sweeps out the whole space. Uniformly 2 convex is this condition here, that the sum of the 2 smallest principal in curvature has to be bigger than a positive constant times the mean curvature. And this is vacuous in 2 dimensions. Okay. And recently, Brendel and Nuff, they have removed this non-collapseness by just, saying an overload. So, and this was what was expected, that overloads are always non-collapsed. Okay, and for the pancakes, we have shown that if you assume rotational symmetry, then there's only one rotational symmetric ancient pancake. And again, this, as Angelos, Kalopoulos, Sesum did, it was a product of being able to have precise asymptotics for the solution. And this asymptotics have been useful for the this work I want to talk about today. So let me just I'm going to describe this ancient pancake, this rotation symmetric, a little bit better. But the next question that we're interested in is to find further examples. So for dimension 2, the only convex examples are this rotation symmetric overload and the sphere. Now for the pancake, we do have this rotation symmetric pancake, but we wanted to see are there more examples. And these were the only ones like missing in dimension 2. Okay. So in higher dimensions, you have to impose this 2 convexity to be able to classify the overload. So we have more of the overloads in higher dimensions as well, or expect to have. But for the pancakes, it's even interesting in dimension 2 to see what other examples there are. Okay, and here's a description of the pancake, which we will use. So this is a picture of the pancake. It can be described by the motion of these 2 points. So here P and this Q. Okay, I'm just going to keep it in dimension n equals 2 to make things simpler. In general, you would have something that is O1 cross ON invariant. Okay, so you can like rotate in more directions, but let's just keep it dimension 2 to make things simple. So in the construction of this pancake, this PT is very close to pi over 2. So this is the pancake that lies in a slab of width pi. And it is actually close to pi over 2. The closeness is any power of t that you want. the mean curvature here at this point PT is the minimum of the mean curvature for the whole surface. Okay, and it is the speed of this point PT, and this is less than any power of t. Okay, this, of course, these two are related because the derivative of PT is the mean curvature at PT. Okay, for QT here, this point, the horizontal point, this guy here moves like minus t plus log of minus t. Forget about this. This shouldn't be there. Okay, forget about this guy. So this is the displacement, the horizontal displacement, and the mean curvature at this point, it is the maximum of the whole surface, and it goes like 1 plus 1 over t. Okay. Let me remind you here that we had the angular oval, which is the one-dimensional example that looks like like one slice here of the pancake. Okay. And this angular oval moves with speed 1. So the maximum curvature is like 1, and the displacement is like minus t. Here, because of the rotational symmetry, we get these additional terms. Okay, so in the examples we've seen the Grim Reaper and the angular oval. They match together because the angular oval is like two Grim Reapers coming together. We have this rotational symmetric ovaloid. This rotational symmetric ovaloid at the tips looks like a ball solidon. A ball solidon is a translator in dimension 2 that is asymptotic to a paraboloid. Okay, so it looks like a paraboloid, and this rotational symmetric ovaloid looks like two ball solidons coming together. Here I am not being precise because you have to, in fact, scale the balls a bit. Okay, you have like also a scaling of the ball as a what is asymptotic here. Okay, so what I mean is that if you look at the ovaloid and you look at a point here, as t goes to minus infinity, the mean curvature goes to 0. But if you scale it appropriately, then what you're gonna see is a ball solid. For the rotational symmetric pancake, here at the tip, as we go to minus infinity, we see a Grim Reaper cross R, which is what we call a grim plane. So this guy here is really like, looks like a bunch of Grim Reapers coming together in a circle from infinity. Okay, in a circle that becomes larger and larger as you go to minus infinity. Okay, so this picture here already shows that the translators can be used as building blocks for ancient solution. Therefore, it makes sense to learn what are the translators first. Okay, so we're looking at translating solutions that satisfy this equation. So I'm looking at translators on the en plus 1 direction. Okay, so the mean curvature has to be equal to the normal dotted with en plus 1. Here, I should have put a minus, but without the minus, think of the upward pointing normal. Okay, so think of a solution that is convex, and the normal is the upward pointing. So we have the grim plane, so Grim Reaper cross R. You can also take a grim plane, tilt it, and scale it. This gives you a translating solution. Okay, the tilt and the scaling should they satisfy this relation. It doesn't really matter, but the one determines the other. And finally, there are these solutions which we call the wing solutions that look like two tilted grim planes at infinity, kind of like a wedge. Okay, but the wedge is done by these two grim planes. And it turns out that in dimension 2, Illman, Hoffman, Martin, and White, they showed that in dimension 2, in fact, these are the only convex ones. Right. Okay. So our what we wanted to construct is the same way. What we take like green planes and we put them in a circle. We created this rotation symmetric pancake. Can one put together these wing solidons, so these wing solutions, to create an ancient solution? Okay, and something like this, say for example, it's not going to be rotational symmetric, but it will have a discrete symmetry. All right, so what we came up how to do this is to use what we call the squash down. So you have a solution MNT and look at omega t to be the interior of MT. Okay, so MT is the boundary of omega t. And we take omega t and we scale it by minus t. So these omega t's, they grow bigger and bigger. Now we scale them down and call this limit omega star. So for example, when I have the angular oval, remember the displacement here is t. So when I scale by t, sorry, by minus t, this will become of length 1, okay, and on the other side as well. The slab bit is going to collapse, and what I see at the limit is just the segment minus 1, 1. For the rotation symmetric pancake, again, when I scale by t, the slab bit is going to collapse, and the circle is a circle of radius minus t plus log minus t, or in higher dimension, I have this constant. So when I divide by t, I'm going to get, I'm just going to get 1, okay? So log of t over t is going to disappear. So the omega star, the squash down of the pancake, is just the sphere of radius 1. Okay, and to be able to justify this squash down, the existence, and that it makes sense, this definition, we have to use a support function. Remember, now we are looking at convex bodies, so the support function at a normal z is the distance of the tangent plane at the point with normal z to 0. Okay, also equal to position dotted with the normal. Right, under mean curvature flow, the support function changes by the mean curvature. So I have d sigma dt equals minus the mean curvature. Remember now z is not, is a normal, right? Using Hamilton's Harnack inequality, we know that for convex solutions, the mean curvature, convex ancient solution, the mean curvature is monotone. So I have the h dt is bigger or equal than 0. And when I use this here, I get the sigma is locally concave with respect to time. This now implies that both this limit exists. So I take the limit of the mean curvature as time goes to minus infinity and the support function over t. And in fact, the two have to be the same. Okay, this is a consequence of sigma being locally concave with respect to time. Then one can play with this, and you get this property. Right. So this gives me that the omega star, as we define as this limit, exists, and sigma star, defined up here, or with the h star z, this should be the support function of the limit omega star. Now, a first observation is the following. If I look at any asymptotic translator at some normal z, what is this? I take my I take a time slice t, and I take the point on this time slice that has normal z, and I put it at the origin. Okay, and for a I'm being a bit sloppy here, but you have to do it for a subsequence of time going to minus infinity. What you get is a translator. It's not difficult to see that the limit is a solution where the mean curvature does not depend on time. Okay, so therefore it is a translator. And it will move with speed equal to h star. Remember, h star is equal to sigma star. So now if you started by, if you consider a solution that lives in a slab of width pi, then you get, as an asymptotic translator, a translator that also lives in a slab of width and most pi. Okay, apologies about that. I live very close to the train. Okay, so now if you think of translators that live in a slab of width pi, because you can use the green plane as a barrier, we have that any such translator should move with speed at least 1. Okay. So the first property that we get about the squash down is that sigma star, the support function of the squash down, has to be at least 1. This means that the unit sphere has to be contained in omega star. Right. So the questions we wanted to answer is what convex bodies omega star can occur as squash down. And if you give me a convex domain, omega star, can I construct a solution with that omega star as a squash down? And again, we've seen this example. Omega star here is the unit sphere. For the wing solution, if you look at omega star, this would just be this would be a circumscribed cone. Okay, so you can see at the picture is going to be a cone, and the relation I had between the with the angle gives me that it's actually a cone that circumscribes the unit sphere. Right. So what are the results that we have here? So we were able to show the following. We were able to construct a convex ancient pancake that's always in a slab of width pi. We squashed down omega star equals p for the following p's. Okay, all the p's have to be circumscribed, meaning that there's a unit sphere in a circumscribed unit sphere. Okay, so we can do P being any regular polytope. This is in any dimension. In dimension 2, think of a regular polygon. And it might be bounded or unbounded. In general, when we say regular, it means that the symmetry group acts transitively on its flags. With the flags is like this sequence of going from faces to edges to corners, okay, or like same with higher dimensions. We can also do any P being a simplex, again bounded or unbounded. So in dimension 2, think of P being any triangle. Okay, and the unbounded simplex would be a cone whose length is a bounded simplex. And finally, a less symmetric but very interesting case is P could be a truncated regular cone. So one can take a cone and cut off a vertex like this. Okay, so this you create a truncated cone, and one can create a solution like this. Now, why is this interesting? Because this gives an example of a non-translating eternal solution. Eternal is a solution that lives for all the time in the future as well. Okay. And it was a conjecture of Brian White since 2003, who claimed that any eternal solution has to be translated. Okay, so this shows that this is not the case. Now, a couple more comments is that all the solutions that we create are reflection symmetric, and the asymptotic translator have the expected Gauss image. What do I mean here is that this picture that I talked about before oops, where was it? See this picture here is indeed the case. Okay, when you go back, you're gonna see the wing solution. Okay, so these are examples where their asymptotic translators are the these wing solutions. Okay, right. Okay, now I'm running out of time, so I'm gonna skip the details of the, well, I only have a rough idea, but I'm just gonna show you the rough idea. So how you construct these things is that you start with your polygon here. It might be unbounded or bounded here on the right, and you go, okay, you scale it so that the circle circumscribed is a radius r, and you attach at each edge a grim plane. Okay, as you attach the grim planes, you're going to create a convex body, which is not going to be smooth, but mean curvature flow is nice enough that it can flow these guys and they immediately become smooth. So this, you do this starting by something of length, let's say r. You create a solution which is old but not ancient, meaning that, you know, it lives for more and more time as r goes to minus infinity. So the idea is to take a limit as r goes to infinity to obtain an ancient solution. Now, when you try to take this limit, you have to be careful that you have some good estimates to be able to take the limit. And the very rough idea is that you start when you start here, you place your grim planes. They do satisfy that mean curvature is bigger or equal that than nu dot v. V is any edge, sorry, not edge, vertex. So this means that your solution is a super solution of the translator equation for every vertex. And a maximum principal argument shows that this is preserved. On the other hand, you have inner barriers by using the rotation symmetric pancake. The rotation symmetric pancake, you can go and place it inside, and it's almost a sub-solution. You have, then it gets a bit technical, but you can use it pretty much as a sub-solution. And you can also get grim planes as outside barriers. So these are very roughly the tools one has to use to construct the solutions. So I'm gonna, let me skip this. Okay, and let's go to the second question, which is what, in general, if you want to look at what is the squash down of a solution, how does it look like? So we were able to show that if you have a convex ancient solution, again, compact or non-compact, it doesn't matter. We only normalize so that it lives in a slab of mid pi. Then the squash down should always circumscribe Sn minus 1. So a picture like here is not admissible. Okay, it should always circumscribe Sn minus 1. Moreover, a further interesting property is that for eternal solution, you can also consider the forward squash down. So I take the same limit, the same ratio, sorry, omega t over t, but now I let t go to plus infinity. It turns out that the forward squash down and the backward squash down have this very nice relation. So here you can see from the picture, if this is omega lower star, the backward squash down, the forward one I obtain by taking every facet or face and moving it on the other side of the sphere that is circumscribed. It is not difficult to see that once you do this, you get a cone, and this cone is the forward squash down. Now this is nice because it gives some very interesting applications. So for example, we can say now that the solution is a translating solution. if and only if the forward and the backward squash down agree, which is also equivalent to saying that the backward squash down is a cone. This property we use to be able to say that the ones we constructed from a truncating cone are not translating solutions. Moreover, we can say that the solution is a green plane if and only if the backward squash down is a half space, and we can show that all two-dimensional solutions are reflection symmetric. Okay. Again, like behind this proof that the existence and the asymptotics of the rotation symmetric pancake are very useful. I'm gonna skip the proof. And let me just finish by saying some further directions. So the question I'm interested in the most to be even more satisfied with this project is to be able to construct a solution for any circumscribed polytope. So as I said, we had this condition that our circumscribed polytope or polygon had to be either a simplex or regular. The problem is that, at least for now, if we start with a quadrilateral and we do this construction when you take like bigger and bigger ones and so on, then we don't know how to save our solution from losing an edge. So it might, lose an edge and still the omega star is circumscribed. So for example, a quadrilateral might become a triangle with 3 of the sides the same. We are also interested to look at uniqueness of solution. So even for the case of S1, so if I have, or this could be in higher dimensions, but if you consider that the squash down is a circle, then we don't know that the only solution is the rotation symmetric one. Or say if you consider that omega star is a triangle, is there only one solution? There we don't even know if you assume some dihedral symmetry, can you say it's unique or not? Then it will be interesting to look at the asymptotic translators. In the construction of the solutions, we knew what the asymptotic translators are, but in general, we don't. This would be interesting or useful for an iterative construction of translators. So I said that the first slide that we have classified it is known now, the classification of translators in dimension 2, but in higher dimension it's still unknown. And finally, we want to do reflection symmetry. We believe it is true for any dimension, the reflection symmetry. But again, because of all of these problems above, we still cannot do it for any dimension. And let me close by saying something like fairly new. So we were able to use this technique for curve shortening flow with a free boundary on the circle, and show that there exists a convex, locally uniformly convex ancient solution to curve shortening flow with free boundary in the disk. So you have like a curve with free boundary, and this we can construct a convex ancient solution, which backward in time it goes to the diameter of the circle. And we're still working on like getting this precise asymptotics for this solution, enabled to so that we will be able to prove uniqueness result. Okay, so thank you very much. Sorry, I said I'm gonna be quicker than an hour, but I went 4 minutes over, so I'll stop here.
Okay, thank you very much. You were quicker than an hour because we started late, so you were right.
Oh, okay.
Are there any? Sorry?
I was worried because I was like, I have to finish that.
No, we finished. We started 10 minutes late, so you were 5 minutes early.
Okay.
So, are there any questions? So you can press the button. About this one with the hand, or just turn on the microphone in case you want to ask any question. Okay, no, I have one question. In the, I think it was the first theorem that you put about the classification of the ancient solutions. The, yeah, very in the beginning, you said that you need to add the embedded
Yeah.
hypothesis, because if not, you had something like flowers.
Yeah. Yeah.
So yeah, I'm going to start this. I'm going to wait.
Yeah.
One before.
Sorry.
This one.
Takes a bit. Yeah. That's too fast now. Yeah.
Yeah, this one, the second one. Yeah. So can you expect any classification result for non-embedded with a large class of examples, or you think that it is not reasonable to have a classification in the non-embedded case?
Oh, no, yeah, maybe I haven't looked at this, but so they know exactly these flowers that I say, they are they are self-similar, right? So they're very nice.
Mm-hmm.
But then Ankinen and a student of his, they've shown that you can, in fact, like put together, you can put together Grim Reapers like in various configurations. So when you say no, you remove convexity and embeddedness, then you can do whatever, you can do a lot of examples.
Okay.
Yeah, so I don't think you can. Yeah, I mean, yeah.
Mm.
Mm.
Yeah. Okay. So, any other question or comment?
I can stop sharing, yeah? No.
Yeah, you can. Okay, so if not, we thank Theodora for the talk. Very nice talk. Thank you very much.
Thank you.
And we thank you all for the assistance to the seminar. And I recall you that next Tuesday, we have Barbara and Ellie's talk at the same hour in the same link. So thank you very much, and I hope to see you next week.
Isabel, I have a question.
Yeah,
do you have us register? What should I register this thing you said